If the idea that the storm itself isn't the most dangerous part, that the real threat begins the moment the wind stops and the lights go out, has you rethinking what it means to be prepared, make sure to hit like and subscribe to Signal Watch so you don't miss a single update as this develops. Drop a comment below. Where are you watching from? What's the worst storm you've ever been through? And tell me, how many days worth of supplies do you have at home right now if the power went out tonight and didn't come back for 2 weeks? If you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You are the reason we can keep chasing stories like this, so thank you for having our back. Now, here's what this investigation is going to cover. In August of 2020, a single derecho traveled 770 miles in 14 hours with winds of up to 140 miles per hour, hitting Cedar Rapids so hard that 95% of the city lost power, some for 2 weeks, and an estimated 7 million trees were destroyed across Iowa alone. $11.5 billion, the costliest thunderstorm in American history. When the June 2012 derecho hit the mid-Atlantic, 34 people died after the storm, not during it, from heat-related illness in the days without power. The storm itself killed 13. The power outage killed more than twice as many. Power transformer demand has surged 116% since 2019. Delivery times that were 4 to 6 weeks as recently as 2020 are now 2 to 4 years. One major U.S. facility has disclosed a 5-year backlog. When the squall line breaks the transformer on your street, the part needed to fix it may not exist yet. And in July of 2023, storms hit St. Louis, and the 911 center received more than 1,000 calls in a single hour. The public safety director said, on record, that the system was completely overwhelmed. A child died waiting for help that was 34 minutes away. And that system is not an outlier. It is the standard. Now, settle in. Let's get into it. Weather in the mid-latitudes, the band of the planet between roughly 30 and 60 degrees north latitude, where most of the United States sits, is supposed to move. That is its fundamental character. The jet stream, that ribbon of powerful westerly winds at approximately 30,000 feet, acts as a conveyor belt, steering weather systems from west to east across the continent. Under normal conditions, a storm system rolling off the Rockies takes roughly 4 to 5 days to cross the country. It arrives. It dumps its rain or snow. It clears. The next system is already forming somewhere over the Pacific, and the cycle continues. No single location sits under the same weather for long. That's by design. That's the physics. But there is a condition in which the physics breaks. It happens when the jet stream, instead of flowing in the relatively straight westerly path that pushes systems across the continent, develops massive meanders. Meteorologists call these Rossby waves, named after the Swedish-American scientist Carl Gustaf Rossby, who first characterized them in the 1930s. Rossby waves are normal. They are a natural consequence of the rotation of the Earth, interacting with temperature gradients between the tropics and the poles. What is not normal is when those waves amplify to the point of stalling. When the meridional flow, the north-south excursion of the jet stream, becomes so extreme that the wave effectively freezes in place. When that happens, something forms that meteorologists call a blocking event. The American Meteorological Society's formal definition of atmospheric blocking requires 3 simultaneous conditions: a persistent obstruction of the normal west to east flow pattern, pronounced meridional flow in the upper levels of the atmosphere, and anticyclonic circulation, clockwise in the northern hemisphere, at high latitudes, accompanied by cyclonic circulation at low latitudes. All 3 conditions together. Persistent. That word is doing enormous work in that definition. A weather system that persists is not just a strong storm. It is a fundamentally different category of meteorological event. It means days. It means weeks. It means the same weather landing on the same soil, the same crops, the same river basin, the same power grid, repeatedly without relief, until something large enough to break the atmospheric lock arrives. Of the various forms a blocking event can take, the one this investigation is concerned with is called the omega block. It gets its name from the shape it produces on upper air weather maps, specifically on the 500 millibar geopotential height chart, which represents atmospheric conditions at roughly 18,000 feet above the surface, the level where blocking dynamics are most clearly visible. When an omega block forms, a massive ridge of high pressure builds in the center, its isobar contours arching upward. On either side, two low-pressure troughs deepen, their contours bowing downward. The whole configuration, high in the middle, lows on either side, traces the shape of the uppercase Greek letter omega. The high is the arch, the lows are the legs. Here is what that means on the ground. Under the high, clear skies, sinking air, no precipitation, temperatures climbing. The sun bakes the surface continuously. Soil moisture evaporates. The land dries. Under the lows, unstable air, rising motion, moisture convergence, clouds, and rain. Not the passing rain of a normal weather system, but persistent training rain, because the low isn't going anywhere. Weather fronts that would normally steer storm systems out of the region are being deflected around the high. They run into the low, wrap around it, and dump their moisture in the same place day after day. Brian Hurley, a senior meteorologist with the National Weather Service's Weather Prediction Center, described the predicament of an active omega block in plain operational terms in May of 2025. It's unclear when the omega block will break down for good, Hurley told Live Science. We're not really seeing that now. What would be required to break it? The jet stream would need to reassert its normal westerly flow, and the block, by its own nature, resists that. The high-pressure center diverts the jet stream around it. The lows on either side feed energy into the blocking structure, sustaining it. The pattern doesn't just persist, it defends its own persistence. Blocks can remain in place for several days or even weeks. That phrase, borrowed directly from the official meteorological literature, is doing the same quiet, devastating work that the word persistent did earlier. Several days or even weeks. Not a storm, not a system, a season within a season. A locked atmospheric configuration that does not care about the infrastructure underneath it, the crops inside it, or the people waiting for it to end. And the specific question this investigation is going to answer, because it has been answered by history, in data, in peer-reviewed research, in documented catastrophe, is this: what happens to an entire country when both arms of an omega block activate simultaneously at full power over the most economically critical terrain in the continental United States? We know exactly what happens, because we've seen it before. In the summer of 2010, most of the world's attention was elsewhere. 2 wars, a global financial system still recovering. The news cycle moved fast, but in the atmospheric science community, something was happening that researchers would spend the next decade trying to fully understand, the most destructive modern example of what an omega blocking event actually does to a country. It began quietly. An unusually warm autumn and spring in 2009 and 2010 set the stage. Above normal temperatures left soil moisture deficits across western Russia before the summer heating season even arrived. Then, in late June, the atmospheric block established itself. High pressure built over western Russia. The jet stream, which normally pushes weather systems through the region in 4 to 5 days, was rerouted around the ridge. A hot, dry air mass settled in over an area the size of Western Europe, and it didn't move for more than a month. The temperature record that had stood in Russia for 1,000 years, according to Alexander Frolov, head of the Rosgodromet State Weather Agency, was shattered. On July 11th, a temperature of 44 degrees Celsius was recorded at Yashkul in the Republic of Kalmykia. Moscow recorded temperatures averaging 40 degrees Celsius during the final days of July and the first days of August, more than 18 degrees above normal. 19 of Russia's 83 administrative regions declared a state of emergency, not from flooding, not from wind damage, from heat and its consequences, drought, fire, crop failure, and the specific human mortality that comes when a modern city's infrastructure is simply not designed to survive weeks of extreme heat. Munich Re, the global reinsurance company that tracks catastrophic events with some of the most rigorous actuarial methodology in the world, estimated that 56,000 people died from the combined effects of the heat wave and the smoke that blanketed Russian cities for weeks as wildfires consumed the desiccated landscape. 1 million hectares of forest and agricultural land burned. Crops didn't fail because of poor management or bad luck. They failed because the block removed all possibility of the precipitation that Russian wheat needs during its critical flowering stage. The numbers that came in from the agricultural sector were staggering. Wheat yields in Russia's top-producing regions, the wheat belt extending across the Central and Volga federal districts, were reduced by more than 70% compared to the previous year. Total national wheat production fell by 20 million metric tons compared to the prior season. By August, the Russian government did something that reverberated through global commodity markets for months. It imposed a wheat export ban. Russia was the world's third largest wheat exporter. When it stopped exporting, global wheat prices moved. Consumers in every country that imported Russian wheat felt it. The damage from one blocking event over one country totaled approximately $15 billion. But here's the detail that William Lau, an atmospheric scientist at NASA's Goddard Space Flight Center, spent years documenting, and that transforms the Russia story from a domestic catastrophe into something that should alarm every person living in a country with a major blocking-prone region. Because at the same moment that Russia was burning, something was happening 900 miles away. Pakistan was drowning. Nationwide rain totals in Pakistan were 70% above normal in July of 2010. In August, they were 102% above normal. The worst floods in Pakistan's recorded history. 20 million people affected. Roughly 2,000 deaths in the acute phase. Economic damage in the billions. These events happened simultaneously. They looked like unrelated catastrophes. A heat wave in Russia, a monsoon disaster in Pakistan, separated by nearly 1,000 miles, and seemingly by entirely different atmospheric mechanisms. Lau and his colleague, Myung Kim, published their findings in the Journal of Hydrometeorology in 2012. The Russian heat wave and the Pakistan floods were physically connected. The Omega blocking event over western Russia excited a large-scale atmospheric Rossby wave train that spanned western Russia, Kazakhstan, and the northwestern China-Tibetan Plateau region. The southward penetration of upper-level vorticity disturbances at the leading trough of that wave train triggered the anomalously heavy rainfall over northern Pakistan. One blocking pattern, two catastrophes, one mechanism. This is the template. This is what an omega block does when it fully activates over a large landmass. It doesn't produce one extreme event. It produces two simultaneously in opposite directions, heat and drought on one side, floods and destruction on the other, linked by the same atmospheric architecture, sustained by the same blocking structure, and completely invisible to anyone watching either event in isolation. The United States is not Russia. It is not Pakistan. But it has the same fundamental atmospheric geography. Large continental landmass, Rossby wave-prone jet stream, massive agricultural heartland sitting directly between the two zones an omega block creates. And it has something Russia didn't have in 2010, a single river system draining 40% of the continental landmass that runs directly through both impact zones simultaneously. The United States has had its omega block years, multiple of them, and while none has yet produced the full simultaneous compound event at maximum intensity, the historical record of the last 15 years provides the evidence base for exactly what each arm of the block does to this specific country, and what both arms together would do. Begin with 2011. By the end of April 2011, most of Texas was experiencing extreme to exceptional drought conditions, the worst possible classifications on the U.S. Drought Monitor scale. David Miskus, who monitored drought for NOAA, described the cause directly. A strong La Niña had shut off the southern pipeline of moisture. By midsummer, nearly three-quarters of Texas had received essentially no meaningful rainfall for months. Evaporation rates at the National Weather Service office in San Angelo measured approximately half an inch per day from April through September. That adds up to nearly 90 inches, 7.5 feet, of atmospheric evaporative demand across a 6-month period, drawing moisture out of soil, crops, and reservoirs faster than any precipitation event could replenish it. 2011 was the driest year ever recorded in Texas, with an average of only 14.8 inches of rain statewide. The Bastrop Fire over Labor Day weekend became the state's most destructive wildfire on record. Crop and livestock losses across the state reached $5.2 billion. The Texas drought of 2011 didn't end when the calendar flipped. It persisted in some parts of the state for 5 more years. And here is what was happening simultaneously in the same country at the same time. In the north, record to near record snowfall had accumulated across a large portion of the northern Rocky Mountains and the northern Plains states during the winter of 2010 to 2011. A cool spring held the snowpack in place longer than usual. Then the melt came, and it coincided with record-setting rains in May and early June over Montana and western North Dakota. The combination sent the Missouri and Saris river basins into historic flooding from June through August 2011. Dam releases above Gavin's Point, the last major dam on the Missouri River before it flows through the Dakotas, Nebraska, Iowa, and Missouri, began in May, exceeding all previous nationwide records for release volume. Minot, North Dakota, a city of approximately 40,000 people, had approximately 1/3 of its homes flooded. Flood, drought, same country, same year, different arms of the same atmospheric architecture. Then came 2012, the year the pattern inverted and the heat arm showed what it could do on its own. A large and persistent area of high pressure developed over the central portion of the nation in late June of 2012 and sat there through the entirety of July. It directed precipitation to the north, across the northern plains and Great Lakes region, while leaving the central part of the nation baking. By July 24th, the drought affected approximately 81% of the contiguous United States, at least some level of dryness or drought conditions across 4/5 of the country. Out of that 81%, 64% met the criteria for at least moderate drought. The U.S. Department of Agriculture, which had been projecting record corn yields for the season just weeks earlier, watched that projection collapse in real time. The final numbers: corn production at 123.1 bushels per acre, against a normal of 166, a 26% decline in a single year. Soybeans down 9%. Hay production damaged. Total agricultural losses across the Midwest reached approximately $35 billion. The drought footprint expanded so rapidly from spring to summer that experts coined a specific term for it: flash drought. And the Mississippi River, the artery that was supposed to carry those crops to market, to the Gulf of Mexico, to export terminals, began to fail from the wrong direction. Not from flooding, from the drought's inverse, record low water levels. The Army Corps of Engineers began blasting the riverbed. The drought of 2012 closed the Mississippi River to barge traffic at least 3 times. 2011, 2012. Flood, drought, north, south, sequential, never simultaneously. But the physics that would produce them simultaneously is the same physics that produced them in sequence. The omega block was there in both years. Its arms were both operating. The only difference was that in those years, they ran one at a time. The agricultural infrastructure, the river system, the power grid, they recovered between events. They had the luxury of sequence. An omega block fully engaged over the continental United States eliminates that luxury. To understand what the flood arm of an omega block actually produces, not in general terms, but in the specific physical terms that determine infrastructure damage, you need to understand one phenomenon in particular: training. In standard weather, convective storm systems, the thunderstorm complexes that produce the heaviest rainfall over the eastern United States form and move. They develop along frontal boundaries, they mature as they track northeast, and they dissipate as they encounter drier air ahead of the front. Any given location might sit under a storm cell for 2 to 3 hours. It gets heavy rain, the cell moves on, another might arrive the next day. The process distributes rainfall across geography over time. Under a stationary low-pressure system, the kind that sits locked in the leg of an omega block, cut off from the steering flow that would normally push it east, that process breaks. New convective cells form repeatedly along the same corridor, following the same track relative to the low. They are drawn into the low's circulation on a consistent bearing. They develop in the same place. They move in the same direction. They dump their moisture over the same watershed. The next cell forms and does the same. This is training, named by analogy to the cars of a train passing over the same point on the track, one after another, each one adding to the accumulation below. The April 18th through 28th, 2011 precipitation event gave a concrete preview of what train convection under a stationary pattern can produce. More than 8 inches of rainfall were recorded at several locations across the central and lower Mississippi Valley during that single 10-day period. At Cape Girardeau, Missouri, the total reached 16.15 inches. Not 16 inches over the month, not over the season, in 10 days. And the subsequent May 16th through 31st event put rainfall totals in portions of the Missouri River subbasin at nearly 1/3 to 1/2 of their entire annual normal amounts in 2 weeks. These events were not under a full omega block at maximum intensity. They were part of the broader spring 2011 pattern. Under a fully established omega block, with the cutoff low parked directly over the Ohio-Mississippi watershed, training convection would repeat not over 10 days, but over 2 weeks, 3 weeks, a month, for as long as the block holds. And the block, as the AMS definition tells us, can hold for several days or even weeks. Here's why the geography directly under this arm matters so profoundly. The Mississippi River and its tributaries drain all or part of 31 states. The basin covers approximately 40% of the continental United States, from the Rocky Mountain slopes in the west to the Appalachian foothills in the east. Every drop of water that falls on that basin eventually makes its way toward the main stem. More than 50 cities depend on the Mississippi River system for their drinking water. Millions of acres of the most productive agricultural land in the world sit in the alluvial plains along its length. When the flood arm of an omega block parks over that basin and trains convective systems across it for 14 to 21 days, the rivers don't just rise, they rise simultaneously from dozens of tributaries, each one delivering its compound peak flow toward the main stem at roughly the same time. There is no upstream first warning sequence. The normal mechanism by which forecasters watch a crest form in Montana and track its arrival in Kansas City 5 days later. There is simply rain everywhere in the basin converging. And underneath those rivers and around them and between them runs the single most important piece of commercial infrastructure in the United States economy. Most Americans don't think of the Mississippi River as critical infrastructure. They think of it as geography, the thing on the western edge of Kentucky, the boundary between Iowa and Illinois, the river Mark Twain wrote about. But in economic terms, the Mississippi River system is infrastructure in the most precise sense of the word. It is the physical mechanism through which the American agricultural economy functions. The numbers are not small. The Mississippi River moves approximately 500 million tons of goods every single year. More than half of all United States grain exports, the corn, the soybeans, the wheat that feed livestock and people on every continent, travel down this river to export terminals near New Orleans before crossing the Gulf to the world. The river system is one of the busiest commercial waterways on the planet, and it is one way. You cannot substitute for it the way you might reroute truck freight around a closed highway. A barge on the Mississippi moves freight at a fraction of the cost of any alternative mode. When the river closes, for whatever reason, from any direction, that freight doesn't reroute at comparable cost. It either waits or it becomes dramatically more expensive. Lou Del Orco, the chief of operations for the Army Corps of Engineers St. Louis District, framed the specific economics of river depth this way. Every time you lose a foot of draft on a barge, that's the equivalent of approximately 6,000 bushels of soybeans you cannot move in that single trip. At drought-era, low water levels in 2012, some stretches of the Mississippi were down 13 feet below normal near Memphis, more than 20 feet below normal near Vicksburg. Barge operators were hauling 15 barges at a time instead of a typical string of 25 and sending them off with drastically reduced loads. Mike Seifert, the CEO of the National Grain and Feed Association, described the economic consequence in plain terms. Barge capacity had already been cut by approximately 50% before the actual river closures even began, and that reduction alone sent barge rates to record levels. Time magazine estimated in 2012 that closing the river entirely could produce losses of approximately $300 million per day, growing exponentially after a few days as supply chains backed up behind the disruption. Deutsche Bank Securities estimated that the 2012 drought's combined impact, including the river commerce disruption, represented a GDP reduction of $75 to $150 billion. Jeff Masters, the co-founder of Weather Underground, wrote that the costs of the 2012 drought would likely dwarf even Hurricane Sandy's damage estimates. And that was from the heat arm alone, the drought arm, without a simultaneous flood arm simultaneously dismantling the levee system and closing the river from the opposite direction. Now apply the omega block's compound structure. The heat arm kills the crops that need to ship down the river. The flood arm closes the river those crops need to ship down. Both arms, simultaneously. The food supply attack runs from both ends of the chain at once. Production collapse on one side, distribution collapse on the other. And it doesn't stop at the borders of the affected states. A peer-reviewed study published in the Proceedings of the National Academy of Sciences in October of 2025 examined exactly this supply chain transmission mechanism. The research found that national food manufacturing is most sensitive to droughts in Midwestern states, specifically identifying Nebraska, Indiana, and Illinois as the most critical nodes. A drought severe enough to fully stress Nebraska's agricultural sector produces an estimated $7.5 billion in cascading losses to national food manufacturing. Indiana at $6.3 billion, Illinois at $5.4 billion. And crucially, the research team found that these losses do not stay in those states. They propagate through the agricultural supply chain to food manufacturers in every state in the country. New Jersey food manufacturers are impacted when Kansas runs dry. Atlanta grocery chains feel a Nebraska drought in their supply costs. The family in Houston buying cereal is downstream of a blocking event in Iowa. The Omega block doesn't just hit the people underneath it, it hits everyone, and it hits them from two directions at the same time. But there is a third system that fails simultaneously, one that, when it goes, makes the food supply disruption, and the river commerce disruption, and the crop failure. Look in the very specific sense of what kills people fastest, like secondary problems. Now consider a squall line 3 times as wide, tracking 1,000 miles through a sequence of major metropolitan areas along multiple storm tracks simultaneously. Consider the same rear inflow jet dynamics, the same cape values, the same bow echo physics. Scaled to a track that doesn't pass through Cedar Rapids once and move on, but hits Kansas City and St. Louis and Indianapolis and Columbus and Pittsburgh and Baltimore in a single continuous event across 12 hours. The utility crews are not waiting in neighboring states, because the neighboring states are also in the storm's path. In August of 2023, the largest power grid in North America, PJM Interconnection, serving 65 million customers from Washington, D.C. to Illinois, issued an emergency alert raising concern about its ability to maintain adequate power reserves as people turned up their air conditioning. Not during an extreme event, during a routine summer heat wave. The grid that serves 65 million people, including the entire Eastern Seaboard's population center, was struggling with a standard summer. Melissa Lott, the research director of Columbia University's Center on Global Energy Policy, described the structural problem in terms that don't leave much room for optimism. We're designing our energy systems today for the past 50 years of weather and not the next 50 years of weather, and that's a problem. Michael Weber, a professor of energy resources at the University of Texas at Austin, put it more plainly: the wires and poles are getting older, and the weather is getting more difficult, and the population's getting bigger. The North American Electric Reliability Corporation, NRC, the organization responsible for overseeing the reliability of North American power grids under the Federal Energy Regulatory Commission, released its long-term reliability assessment on January 29th of 2026. The document projects that summer peak demand will surge by 224 gigawatts over the next 10 years. That number is 69% higher than NERC's own projection from the previous year. The compound annual growth rates for both summer and winter peak demand are, in NERC's own characterization, the highest since they began tracking this metric in 1995. Data centers for artificial intelligence applications, industrial electrification, and the broader shift away from fossil fuel heating are combining to produce a demand curve that existing generation and transmission infrastructure was simply not designed to meet. This is the grid that an Omega Block's heat arm attacks first. Sustained heat in the 90s and 100s drives cooling demand that stacks load onto a transmission system already running near capacity margins. Grid operators begin managing reserves. Emergency demand reduction requests go out. Utilities ask large industrial customers to voluntarily curtail. And if the heat persists, as it does under a blocking event, day after day, without the relief of a cooling front that would normally arrive in 48 to 72 hours, those conservation measures run out of headroom. What comes next is rolling blackouts or targeted load shedding, but the heat arm's demand surge is only the first attack. The flood arm runs the second one simultaneously. Climate Central's analysis of major U.S. power outages from 2000 through 2023 documented that severe weather, defined as high winds, rain, and thunderstorms, caused 58% of all weather-related power outages over that period. The flood arm of an Omega Block is, by design, a continuous severe weather machine. The cutoff low sitting in the eastern trough is generating training thunderstorm complexes, the same systems, the same tracks, day after day. Each one brings high winds that knock down transmission lines. Each one brings lightning that strikes transformers and substations. Each one brings flooding that inundates underground distribution infrastructure and the ground-level facilities around transmission towers. The flood arm is physically dismantling the grid at the same moment the heat arm is pushing demand above it. The numbers on this trend are not reassuring. Americans experienced approximately twice as many weather-related power outages during the 10 years from 2014 to 2023 as they did during the 10 years from 2000 to 2009. Heat season outages, those occurring between May and September, increased by approximately 60% over the same comparison period. Major blackout events, those affecting at least 50,000 customers for at least 1 hour, increased by more than 60% over the most recent 5-year reporting period. The grid is not getting more resilient. It is getting more stressed in more weather conditions, more often. Now add the compound event research. A peer-reviewed study published in Environmental Science and Technology in 2021 examined what happens when blackout events coincide with heat waves in 3 major U.S. cities: Atlanta, Detroit, and Phoenix. The researchers modeled interior building temperatures during a simulated compound event, blackout plus heat wave simultaneously, using the weather research and forecasting regional climate model combined with an advanced building energy simulation. The finding was direct and quantified. In Atlanta, Detroit, and Phoenix, between 68 and 100% of the population would face elevated risk of heat exhaustion or heat stroke during a combined blackout and heat wave scenario. Not some percentage, not a vulnerable subset, 68 to 100% of the entire urban population. A 2023 study went further on the Phoenix case specifically. It estimated that if a multi-day blackout coincided with a heat wave, nearly half of Phoenix's population would require emergency department care for heat stroke or other heat-related illness. The study's estimate for fatalities under those conditions, approximately 12,800 deaths. In one city, in one event, 12,800 deaths. In Phoenix, alone. Now scale that across every major city sitting under the heat arm of an omega block. Dallas, Kansas City, Oklahoma City, Denver, Wichita, each of them experiencing the same sustained high temperatures, the same demand surge pushing the grid toward its limits, while simultaneously, in the flood zone to the east, thunderstorms are tearing down the transmission infrastructure those cities depend on for power. Both arms, same moment, the demand attack and the physical destruction attack running in parallel. The grid was not designed for this. The planning documents that govern grid reliability were built around historical weather patterns. The past 50 years, as Melissa Lott said, an omega block at full activation is not the past 50 years of weather. It is the compound scenario that every NERST reliability assessment frames as a tail risk, a low probability extreme. But tail risks don't stay in the tail forever. And when this one arrives, the compound event research says it will not announce itself with a single dramatic failure. It will arrive as a heat dome that won't leave, a storm system that keeps training on the same territory, and a grid that runs out of room to absorb both simultaneously. The question that this investigation cannot avoid, the one that determines whether an omega block is a severe week of weather or a multi-week catastrophe, is why does it persist? What is the mechanism that sustains it? And is there anything about the current state of the atmosphere that makes persistence more likely than it used to be? The answers are connected, and they are documented in the research literature with enough specificity to construct a precise physical picture. Start with the heat arm, because it is doing something that goes beyond passively baking the landscape. As the blocking high sits over a region and suppresses precipitation, it dries the soil. Under normal conditions, a significant fraction of solar energy arriving at the Earth's surface is consumed by evapotranspiration, the process by which plants and wet soils transfer moisture to the atmosphere as water vapor. This process requires enormous amounts of energy. It acts as a natural air conditioner for the land surface, moderating temperatures even in the presence of intense sunshine. When the soil dries completely, when field capacity has been exhausted, and there's no longer moisture available for evapotranspiration, that buffering mechanism disappears. All incoming solar radiation goes directly into sensible heat. Air temperature, the surface heats without limit. And a hotter surface means more intense, deeper, stronger high pressure, which means a more resistant, more self-sustaining block. This feedback mechanism was specifically documented in the 2010 Russian event. The IOP science paper published in 2020 identified it precisely. The Russian heat wave was amplified by a positive feedback through changes in surface energy fluxes between the atmospheric blocking pattern and an underlying extensive land region with below normal soil moisture. The land was already drier than normal going into the event. The block dried it further. The drier land amplified the block. The amplified block resisted breakdown longer, and the longer the block held, the more the land dried and the deeper the feedback ran. The initial soil drying in June and early July of 2010 was, in the research literature's assessment, a major cause of the exceptional heat levels that emerged after mid-July. The soil wasn't just a victim of the heat wave. It was an active participant in making it worse. Now look at the flood arm. For decades, meteorological research focused primarily on the dry dynamical processes that sustain blocking, the movement of air masses with low potential vorticity from the subtropics into the blocking structure, the behavior of Rossby waves at the tropopause level. But more recent work has identified a second pathway that was systematically underappreciated: moist dynamical processes. When the cutoff low on the flood arm side draws in moisture from the Gulf of Mexico through the low-level jet that is the Great Plains' primary moisture transport mechanism, that moisture rises in what meteorologists call a warm conveyor belt, a broad ascending airstream ahead of the low. As the moisture rises, it condenses, forming clouds and producing the training rainfall events that hammer the eastern watershed. But the condensation also releases latent heat, and that latent heat release, high in the troposphere, builds and maintains a potential vorticity structure that reinforces the blocking pattern. The flood arm isn't just a passive output of the omega block. It is partially fueling the block itself. The moisture it draws in, the rain it produces, the latent heat it releases, all of it feeds back into the atmospheric structure that keeps the block locked in place. A 2025 research paper specifically studying omega blocking events with compound extremes documented that this moist pathway is now understood to be a critical, if historically underappreciated, driver of block maintenance. What this means in practical terms, the two arms of the omega block reinforce each other's persistence through physically distinct mechanisms. The heat arm dries the soil, eliminating the surface buffering that would moderate temperatures and reduce the pressure anomaly. The flood arm draws moisture into ascending air streams that release latent heat at altitude, feeding the potential vorticity structure of the block. Neither arm is weakening the block. Both are sustaining it. And one more factor, documented in a 2021 paper in Nature's Climate and Atmospheric Science by D. Capua and colleagues studying the 2010 event specifically. The sea surface temperature anomalies in the tropics can increase the probability of this kind of wave train by a factor of 2 to 4 relative to what climate models predict as the background probability. The models already underestimate block formation probability. The warm ocean state makes it worse by another factor of 2 to 4 on top of that. The block doesn't just resist breakdown. It is designed by the physics of its own existence to last. And this is where the story takes a turn that the official emergency response planning documents have not yet caught up to. American emergency management at the federal, state, and local level has been built around a fundamental organizing assumption. Disasters are local, they are acute, and they end. A hurricane makes landfall in a specific coastal zone. It causes catastrophic damage in a defined footprint. Resources from unaffected states, National Guard assets, FEMA teams, utility restoration crews flow into the impact zone from every direction outside it. The affected population is supported by the unaffected majority. The mutual aid system, which is the backbone of every state-to-state emergency assistance agreement in the country, depends entirely on geographic redundancy. It depends on there being somewhere outside the disaster zone from which help can come. An omega block eliminates that assumption at the continental scale. When the flood arm runs from Maine to Georgia, training storm complexes over the Ohio and Mississippi River watersheds for 2 weeks straight, and the heat arm simultaneously parks over the central U.S. from Texas to the Dakotas, there are no unaffected states. There is no pool of mutual aid resources standing by at a safe distance, ready to deploy. Every state under the heat arm is managing its own heat emergency, its own demand-stressed grid, its own crop failure crisis. Every state under the flood arm is managing its own flooding, its own levee stress, its own road closures and evacuation operations. And the states between the arms, those straddling the transition zone where flooding meets drought, are managing both. The Federation of American Scientists published a paper in 2024 specifically examining the scenario of widespread grid failure under extreme heat. The authors found that no coordinated interagency memorandum of understanding exists for managing a widespread, multi-state grid failure coinciding with extreme heat. Not a policy gap, not a funding shortfall. A structural absence, the planning framework for this specific compound scenario has not been written. Consider what NOAA documented for 2023, 28 weather and climate disasters, each causing at least $1 billion in damage, a new annual record, surpassing the previous record of 22 in 2020. Combined cost, at least $92.9 billion. 28 separate events across the calendar year, each one drawing from the mutual aid pool, each one requiring FEMA coordination, state emergency management activation, National Guard deployment. 28 events spread across the year taxed the system to a level that set records. An omega block doesn't produce 28 events. It produces one pattern, 2 simultaneous catastrophes. The mutual aid pool doesn't replenish between them. Emergency management systems that were fully activated for the flood arm on Monday are still activated when the heat arm peaks on Thursday. Utility restoration crews that have been deployed to storm damage in Ohio are not available for rolling blackout triage in Texas. The logistical architecture of American disaster response, built around sequential events with recovery periods between them, has no protocol for the simultaneous demand. NERC has issued 11 reliability warnings over the past 5 years. 11. The warnings have been clear, specific, and incrementally more urgent with each cycle. Demand is growing faster than generation capacity is being added, dispatchable, generation is retiring, and the grid is increasingly exposed to weather conditions more extreme than its design envelope assumed. In the summer of 2023, the MISO grid, which serves the central United States from Minnesota to Louisiana, averted a shortfall only because a period of extreme conditions was shorter than projected. Averted, not managed. Averted. The word avert in a NERC reliability report is not reassuring. It means the system functioned because the extreme scenario was shorter than modeled. Under an omega block, the extreme scenario is not shorter than modeled. It is longer. It is, by the block's own self-reinforcing physics, designed to outlast the modeling window the grid was planned around. The emergency management system is not ready for this, not because the people in it are unprepared or the agencies are incompetent, because the planning framework was built around a world where disasters arrive one at a time, in one place at a time, and end on a predictable schedule. The omega block is none of those things. It is everywhere in its impact zone simultaneously. It covers an area that eliminates geographic redundancy, and it ends when the atmosphere decides, not when the calendar, the model, or the emergency management plan says it should. There is a dimension of the omega block's flood arm impact that doesn't appear in the rainfall totals or the river gauge records alone. It appears in the relationship between the event and what came before it, what the land was carrying going in. The research literature on the 2011 Missouri River flood is instructive here in a specific way. A study led by Martin Hurling and colleagues examining the record flooding's causes identified 3 compounding factors: antecedent wet conditions that preconditioned the upper basin toward greater runoff efficiency, a cold and wet winter with unusually high snowpack, and heavy rains in late spring that were the immediate trigger, all 3 together. Remove any one of them and the flood is less severe. Remove the antecedent moisture, the land being already wet before the event began, and the same rainfall produces a manageable flood season rather than the worst Missouri River flood on record. The land conditions going in determine the event's severity, not the storm alone, the storm plus the land it arrived on. The 2010 Russian event showed the same dynamic running in the opposite direction. The soil drying that preceded the block's most intense phase, the below normal moisture conditions that established themselves before temperatures spiked, amplified the heat and drought to levels that the atmospheric forcing alone would not have produced. Dry land plus blocking high equals catastrophic heat. Wet land plus stationary low equals catastrophic flooding. The same physical principle, operating in both arms simultaneously. Antecedent conditions are the silent multiplier. Drought.gov, the federal portal maintained by NOAA, the USDA, and multiple partner agencies specifically for monitoring drought conditions in major river basins, framed the 2011 to 2012 succession in stark terms. It was precisely the floods of 2011 and then the extreme and rapidly evolving drought of 2012 that demonstrated the scale of the vulnerability. A region that had been in record flooding entered the following season in record drought. The Missouri River Basin went from the highest flows in its modern recorded history to the most severe drought of the 21st century in the span of less than 12 months. The Drought.gov team specifically noted this pattern as the reason an early warning system was needed, because the transition from one extreme to the other can happen faster than the planning cycle can respond. Now layer the precipitation trend data onto this picture. The National Centers for Environmental Information's extreme wetness analysis of the Missouri River Basin documented that basin-wide precipitation has increased by approximately 8% since 1895, with spring precipitation up 14% over the same period. The basin is, on a statistical basis, wetter going into spring weather events than it was a century ago, more soil moisture, more snowpack in wet years, more pre-saturated ground, waiting to convert every inch of training rainfall directly into runoff. The antecedent conditions that amplified the 2011 flood are systematically more favorable for catastrophic outcomes than they were even a generation ago. The flood arm of an omega block doesn't just deposit rainfall on a neutral landscape. It deposits rainfall on a landscape that is already carrying its own history of prior events. A history that, in the Missouri and Mississippi basin, has been trending toward more moisture, more vulnerability to rapid saturation, and more infrastructure stress going into each new event. The margin for absorbing the flood arm's output gets thinner with each decade of the precipitation trend. What the land can absorb goes down. What the block produces goes on to an ever smaller buffer. And when the buffer empties, as it does within the first few days of any extended training event, every subsequent raindrop becomes direct river rise. The self-reinforcing block, the antecedent saturation, the river system draining 40% of a continent, the food supply running through it in both directions, the power grid stressed from two sides simultaneously, the mutual aid architecture built for one disaster at a time. Every component of this investigation has been building toward the same compound picture. And the question this investigation now has to answer honestly is what specifically the most likely outcomes look like, and what data would distinguish between them. The storm gives you the warning when it chooses to give it. The infrastructure failure that follows begins the moment the storm passes. And as the investigation has now established, the parts to fix the infrastructure are on a 2-year backlog. The 911 system is overwhelmed within the first hour, and the heat that killed 34 people in 2012 is returning in 48 hours, whether the power is back or not. The 30-minute warning window and the multi-week recovery timeline are happening to the same families, in the same homes, without a plan for either one. Every weather forecast you've ever received on your phone from your local meteorologist from the National Weather Service website is produced by numerical weather prediction models. These are large, computationally intensive systems that ingest observational data from weather balloons, satellites, ground stations, aircraft, and ocean buoys, then solve the dynamical equations governing atmospheric fluid flow to project future atmospheric states. For single system events, a cold front sweeping southeast, a developing hurricane, a bow echo moving across the Ohio Valley, these models are extraordinary. Modern forecasts for individual storm systems are skillful out to roughly 10 days for large-scale patterns, a scientific achievement that would have seemed like science fiction to the forecasters of 50 years ago. But blocking events sit at the boundary of what these models can reliably do. And the research literature on this boundary is unusually candid about where the capability ends. Skybrary, the authoritative aviation safety meteorology resource maintained by Eurocontrol and the FAA, states this directly in its formal treatment of omega blocks. The onset and decay of these events is still not well captured in numerical weather forecasts and remains an open area of research, not a limitation expected to be resolved soon, not a problem with a known solution pending implementation. An open area of research. The models are working on physics they don't yet fully understand. The American Meteorological Society's peer-reviewed literature characterizes the problem at the level of fundamental dynamics. Atmospheric blocking is a phenomenon that is not fully understood in terms of the underlying physics. The patterns that cause it, the feedbacks that sustain it, and the triggers that break it, all of these are active research frontiers. The AMS definition tells us what blocking looks like when it's there. It cannot yet tell us, with the precision operational forecasting requires, when it will arrive, how long it will last, or when it will end. Brian Hurley, a senior meteorologist with the National Weather Service's Weather Prediction Center, illustrated this operational reality in May of 2025 during an active omega block over the central U.S. The block could temporarily break down, Hurley acknowledged, but the atmospheric pattern would likely reinstate itself. When would it break down permanently? It's unclear when the omega block will break down for good, Hurley told Live Science. We're not really seeing that now. And what would it take? The jet stream would need to reassert its normal westerly flow. But, and this is the critical operational point, we're not really seeing that now? That's not a forecast. That's an honest description of the limit of the forecast. And it's the description that emergency managers, utility operators, agricultural traders, and millions of families trying to plan for the week ahead are actually working with. Here is the specific mechanism that breaks model skill during blocking. The numerical forecast models treat blocking through their representations of large-scale wave dynamics, the propagation and amplification of Rossby waves at the tropopause level, the potential vorticity anomalies that define the blocking structure. For the dry dynamical pathway, the transport of low-potential vorticity air from the subtropics into the block via near tropopause air streams. The model physics is reasonably well represented, though still imperfect. The moist dynamical pathway is where the systematic model error lives. When warm, moisture-laden air rises in the warm conveyor belt ahead of the flood arm low, it releases latent heat at altitude. That latent heat release affects the potential vorticity structure of the atmosphere in a way that feeds the block. Current operational NWP models, the GFS, the NAM, even the ECMWF, represent these moist processes through parameterization schemes, simplified mathematical approximations of physical processes too complex to compute directly at the model's spatial resolution. And parameterization of moist convective processes is among the most uncertain components of modern NWP. The consequence? Models systematically underestimate the moist pathway's contribution to block formation and maintenance. They therefore systematically underestimate both the probability of block formation in the first place and the persistence of the block once it forms. The research by Dai Kapua and colleagues, published in Nature's Climate and Atmospheric Science in 2021, quantified this model gap directly for the 2010 event. Sea surface temperature anomalies in the tropics during that summer increased the probability of the Russian wave train, the specific atmospheric configuration that produced both the heat wave and the Pakistan floods, by a factor of 2 to 4 relative to the model's base climatological probability. The model said the event was this rare. The actual atmosphere, informed by sea surface temperature conditions the model wasn't fully capturing, said it was 2 to 4 times more likely than that, a factor of 2 to 4 on probability. That's not a rounding error. That's the difference between planning for a 1 in 50-year event and a 1 in 15-year event. It changes infrastructure investment decisions. It changes agricultural insurance pricing. It changes the threshold at which emergency managers activate pre-positioning resources rather than monitoring conditions. And the most recent research, examining Greenland blocking specifically, a pattern closely related to North American omega blocks, found that the CMIP6 models used for climate projection generally fail to capture the increase seen in observations and underestimate blocking variability. The observational record shows blocking events are becoming more frequent and more intense in some regions. The models say they're not. Both statements cannot be simultaneously correct, and history, as a rule, sides with observations over models when the two diverge. The forecasting system isn't wrong because the people building it are careless. It's wrong because the physics of moist blocking dynamics pushes against the mathematical limits of what parameterized numerical weather prediction can currently represent. The models will improve, but improvement takes years of research, validation, and operational testing. Right now, today, the forecast for an active omega block tells you something bad is coming. It cannot tell you how bad. It cannot tell you how long. And it cannot tell you when it ends. There is a specific kind of damage that the heat arm of an omega block produces that doesn't appear in the acute weather records, the temperature maximums, the heat index peaks, the single-day death tolls. It appears in the cumulative record, the damage that accumulates not from any single extreme day, but from the relentless, unbroken sequence of days that a blocking event sustains. The 2012 heat dome is the most instructive example, precisely because it was so extensively documented. From late May through early August, approximately 10 weeks, a high-pressure system developed and persisted over the northern Atlantic Ocean, effectively locking in a hot, dry weather pattern across most of the nation, as the Science Direct drought analysis characterized it. Within that sustained pattern, two distinct embedded heat waves emerged, one starting in late June, one during the second half of July. The researchers identified these specifically as especially harmful to grain corn, not because the temperatures on any single day exceeded historical records in most locations, but because of timing. Corn is acutely vulnerable during pollination, the window during which a corn plant undergoes pollination. When the silk emerges from the ear and must receive pollen to develop grain, lasts approximately 10 days. If temperatures exceed approximately 95 degrees Fahrenheit during those 10 days, pollen viability drops sharply. If nighttime temperatures don't fall below 70 degrees, the plant's stress response kicks in and it begins aborting kernels. A single day of extreme heat during pollination is damaging. 10 consecutive days during which daytime temperatures routinely exceed 95 and nighttime temperatures stay in the mid-70s, which is exactly what the embedded heat wave within the block produced, is potentially catastrophic. The USDA had been projecting record corn yields for 2012 as late as April of that year. Planting pace had been the earliest in modern records. Corn planting was 20% complete by April the 17th, the earliest date on record, and surpassed the halfway mark before the end of April. The season looked exceptional. Then came the block. The corn yield came in at 123.1 bushels per acre, a 26% decline from the 166 bushels that constituted normal expectations. The entire projected record harvest didn't just fail to materialize, it fell to the worst yield since the drought years of the 1950s, and this was one commodity from one arm in 1 year. Soybeans fell 9%. Hay production dropped across the affected region, cutting into livestock operations. The drought was declared a natural disaster in 2,245 counties, 71% of the entire United States. Total agricultural losses reached approximately $35 billion in the Midwest alone. The San Angelo, Texas case from 2011 provides the other end of the temperature spectrum, the cumulative evaporation dimension of the heat arm's damage that rarely gets quantified. National Weather Service measurements at San Angelo documented evaporation rates averaging approximately half an inch per day from April through September of 2011. That adds up to nearly 90 inches, 7.5 feet, of atmospheric evaporative demand over that 6-month period. Evaporation is not rainfall. It is moisture being actively pulled out of the landscape. Soil that was already dry by April was bone dry by June. Rivers that were running low in May stopped running in July. Lakes that had never gone dry in modern records exposed their beds. Now apply the Russia 2010 global market connection to the U.S. heat arm scenario. When the Russian government imposed its wheat export ban in August 2010, it did so because its wheat belt had seen production fall by 20 million metric tons in a single growing season. The global wheat market, which operates on relatively thin surplus margins in any given year, responded immediately to the removal of Russia's export volume. Prices moved. Countries that imported Russian wheat faced supply uncertainty. The cascade from one blocking event in one country to food price instability in grain. Importing nations around the world happened within weeks of the export ban's announcement. The United States is not Russia in scale of wheat production, but it is the world's largest exporter of corn and soybeans. A 26% decline in corn yield, the magnitude documented in 2012 from the heat arm alone, without a simultaneous flood arm degrading the distribution system, produces market signals that travel far beyond the Midwest. Food price increases in the U.S. become food price increases globally because the U.S. export market sets marginal prices. The PNAS 2025 research confirmed this transmission mechanism domestically. Drought losses in Nebraska propagate to food manufacturers in New Jersey. The international version operates on the same logic, through export markets rather than supply chains. The heat arm, sustained for 10 weeks over the corn and soybean belt, doesn't just damage the harvest. It doesn't just spike domestic food prices, it alters the global food supply calculation for the season, because the U.S. is the supplier of last resort for a portion of the world's grain imports. And when the U.S. supply contracts sharply, the global market has nowhere to absorb the shortfall except through price. Everyone, as the title of this episode states, is affected, not in the same way, not to the same degree, but downstream of the heat arm's damage is every household in America buying groceries, every food manufacturer sourcing grain, and every country that looks to the United States for agricultural exports. This is where the investigation assembles all of its evidence into a single operational timeline, because the way an omega block's compound failure actually unfolds is not random. It follows the physics of each arm, and the physics of each arm has a timeline. Days 1 through 3, the block establishes. The 500 millibar geopotential height maps show the high-pressure ridge building over the central United States, the two flanking troughs deepening on either side. The 7-day forecast begins showing above normal temperatures in the center and above normal precipitation in the east and west. But the forecast ensemble spread is wide because the models are already in their documented failure mode for blocking onset. Some ensemble members show the pattern breaking in 5 days. Others show it holding for 2 weeks. Emergency managers see the elevated risk flags, but cannot justify pre-positioning major resources against uncertain model guidance. The public sees a forecast that says rain is coming. Normal rain, maybe a lot of it. Days 4 through 7, the flood arm is producing its first significant rainfall events over the Ohio and Mississippi watersheds. The training pattern hasn't fully established yet. This phase looks like a persistent low, not yet a fully locked block. But soil moisture monitors in the Missouri, Ohio, Mississippi basin, if anyone is watching them closely, are already showing rapid accumulation. River gauges are beginning to trend upward. In the center, the heat arm is establishing. Temperatures 3 to 5 degrees above normal, not yet extreme. Power demand is elevated. Crops under the heat arm have received no meaningful rainfall since the block locked in, and the soil moisture in the Corn Belt is beginning its descent. Farmers are watching. Days 8 through 14. This is where the event diverges decisively from anything the standard planning framework was designed for. The flood arm is now in full training mode. Convective complexes forming repeatedly along the same tracks, depositing rainfall on watershed soils that are approaching field capacity. The Ohio tributaries are above flood stage in multiple locations. The first Missouri River gauges are responding. Road closures begin. In the center, the heat arm is producing its first embedded heat wave. The sustained multi-day period of temperatures above 95 degrees that the 2012 data identified as especially harmful to grain crops during pollination. Power demand across the heat arm's footprint is at or above summer peak records. NERC grid operators are managing reserves. The grid is absorbing the demand surge for now. Day 10, the critical marker. In the research literature, 10 to 14 days is where the omega block's self-reinforcing mechanisms have had time to fully engage. The heat arm has dried the soil under the high, reducing evapotranspiration, pushing more solar energy directly into surface temperature, deepening the blocking high. The flood arm's warm conveyor belt airstreams are releasing latent heat at altitude, feeding the potential vorticity structure that maintains the block. The models, rerunning their ensembles with the updated observational data, are showing longer persistence than their day 1 guidance suggested. Emergency managers are now seeing model guidance that they didn't see at day 1, but they're seeing it on day 10, after the event has been running for 10 days, not before it started. Days 14 through 21. If the block has reached this duration, the event has crossed into a domain that no U.S. infrastructure system was designed to handle. The flood arm's training rainfall has saturated the Missouri, Ohio, Mississippi watershed. every subsequent inch of rainfall is direct runoff. River gauges along the Missouri main stem are at or approaching major flood stage simultaneously, not the sequential upstream to downstream crest sequence that gives forecasters lead time, but simultaneous cresting across the basin because the rainfall is simultaneous across the basin. Levee sections flagged in Army Corps assessments as vulnerable are under active stress. The cascade begins. At the same time, the heat arm has now been running for 2 weeks. The corn crop's pollination window has been compromised. USDA field surveys are beginning to show the yield damage. Food price futures markets are moving. Cattle operators under the heat arm are running out of forage and water. Meanwhile, the thunderstorm complexes rotating through the flood arm are generating sustained wind events and lightning strikes that are cumulatively dismantling transmission infrastructure across the eastern impact zone. Substations are flooding. Transmission towers are down in multiple corridors. The grid is trying to reroute power around the physical damage while simultaneously managing the demand surge from the heat arm's heat. It is being attacked from both sides. Day 21 and beyond. The compound failure is now operating across all 3 dimensions simultaneously. The food supply chain is compromised from both the production end and the distribution end. The power grid is experiencing localized blackouts in the flood arm's footprint from physical damage while approaching demand limits in the heat arm's footprint. Emergency management systems across both zones have been activated for 2 to 3 weeks with no mutual aid reserve. Because every state inside the block's footprint is affected. The planning framework that governs every state-to-state mutual aid agreement in the country depends on geographic redundancy that the block has eliminated. There is no historical event in U.S. records that produced this combination simultaneously. But the physics that would produce it is documented. The historical events that produced each component in isolation are documented. The Russia-Pakistan 2010 event produced the compound template over a different geography, and the self-reinforcing mechanisms that would sustain it are documented in peer-reviewed literature with enough clarity to trace the timeline above without speculation. Just physics applied to known infrastructure. I want to address something directly because it deserves an honest answer grounded in physics rather than dismissal. Whenever the atmosphere produces something as extreme, as large-scale, and as poorly predicted by official models as an omega blocking event, particularly one that affects food prices, power reliability, and emergency response capacity across an entire country, a set of claims begins circulating. The specific claims vary, but they follow a consistent structure. This event was manufactured, the drought was engineered, the flooding was directed. Some government or private entity using technologies like HARP or directed energy weapons or classified atmospheric manipulation systems is producing these conditions for political or economic purposes. These claims fail on physics, not on trust, not on politics, on the specific quantified relationship between energy inputs and atmospheric outcomes. HARP, the High Frequency Active Auroral Research Program, operated by the University of Alaska Fairbanks, is a real facility. It conducts real research on ionospheric physics. Its maximum power output is approximately 3.6 megawatts. The ionosphere it studies is located at approximately 60 miles altitude. The jet stream is located at 5 to 9 miles altitude, more than 6 times lower than where HARP operates, separated by 50-plus miles of atmosphere, and entirely different physical processes. The energy required to deflect the jet stream, to push a river of wind moving at 100 miles per hour, across a corridor thousands of miles wide by even a single degree of latitude, is measured in petajoules. 1 petajoule is 10 to the 15th joules. 1,000 trillion joules. HARP's maximum sustained output over an entire month at full power is approximately 3 gigajoules, 10 to the 9th joules. The ratio of what deflecting the jet stream requires to what HARP produces is approximately 1 million to 1. You cannot steer the jet stream with a radio transmitter any more than you can move a freight train with a bicycle. Cloud seeding, silver iodide introduction into supercooled cloud cover, is a real technology with real, documented effects on precipitation. Under optimal conditions, 5 to 15% enhancement of precipitation in targeted cloud cover. The flood arm of an omega block is producing training rainfall events that deposit 16 inches over 10 days. Cloud seeding doesn't create those cloud systems. It cannot sustain a cutoff low for 3 weeks. It operates at county to regional spatial scales, not synoptic atmospheric scales. Now let's address the attribution of the specific historical events this investigation has drawn on. Randall Dole, the deputy director of NOAA's Earth System Research Laboratory, led the team that studied the 2010 Russian heat wave. His conclusion, published in peer-reviewed literature: the Russian heat wave was primarily due to a natural phenomenon called atmospheric blocking. His team studied both historical observations and computer model simulations and found that the event was driven by natural atmospheric variability, with the specific blocking structure arising from Rossby wave dynamics in the upper atmosphere. David Miskus, NOAA's drought monitor, attributed the 2011 Texas drought directly to La Niña conditions. The periodic cooling of equatorial Pacific sea surface temperatures that suppresses precipitation in the southern plains. La Niña is not a government program. It is an ocean atmosphere coupled oscillation driven by solar heating patterns and equatorial trade wind dynamics. No government agency can create La Niña. No technology can sustain it. It is what it is. The real human fingerprint in this story, the one that doesn't require a conspiracy to explain and is documented in the scientific literature, is atmospheric. The University of Georgia research team, led by Jonathan Preece and published in Nature Communications in 2023, documented that increasing waviness in the jet stream, together with the decline in North American snow cover, is favoring these blocked high-pressure systems over Greenland, and by extension, over the North Atlantic region that influences U.S. weather patterns. The mechanism is the reduced meridional temperature gradient between the tropics and the poles as high latitudes warm faster than the global average. A warmer Arctic relative to the tropics means a weaker thermal gradient. A weaker thermal gradient means a weaker, wavier jet stream. A wavier jet stream is one that develops the large amplitude Rossby wave excursions that can amplify into blocking events. Climate Signals has identified an anthropogenic component in multiple recent blocking events, including the 2010 Moscow heat wave, the 2011 Texas-Oklahoma drought, and the 2011 to 2016 California drought. Not manufactured. Amplified. The background warming that increases atmospheric water vapor via the Clausius-Clapeyron relation, approximately 7% more water vapor capacity per degree Celsius of temperature increase, makes the flood arm's rainfall heavier when it occurs. The reduced temperature gradient that produces more persistent jet stream waviness makes the block more likely to form and harder to break. Those are the mechanisms. They have named authors, published datasets, and peer review behind them. The conspiracy explanation is wrong, and the actual physics, a wavier jet stream, amplified blocking probability, heavier precipitation under flood arms, more intense heat under heat arms, is alarming enough without embellishment. The real story doesn't need the conspiracy. The ordinary physics is devastating enough on its own. Jennifer Francis, a researcher at the Woods Hole Research Center who has spent decades studying this relationship, described the mechanism. The Arctic warming faster than the tropics reduces the temperature contrast that drives the jet stream's strength. A weaker jet stream is a wavier jet stream. A wavier jet stream creates more frequent and more extreme excursions of cold air southward. Exactly the kind of out-of-season Arctic intrusion that, when it meets Gulf heat, produces the conditions for a catastrophic squall line. The real story doesn't need the conspiracy. The ordinary physics, documented, published, named, is alarming enough on its own. The governing variable, the single measurement that determines which of the three outcomes below materializes, is block persistence duration. How long the atmospheric lock holds. Everything else in this investigation flows from that number. The total rainfall under the flood arm, the cumulative heat stress on the crop, the grid demand days above critical thresholds, the number of levee sections sequentially stressed, the duration of mutual aid system depletion. The block's duration sets every downstream number. And as this investigation has established, that number is the one the models are least equipped to predict. Here are the 3 outcomes the evidence supports, presented honestly, without predetermined conclusions. The governing variable, the single measurement that determines which of the 3 outcomes below materializes, is block persistence duration, how long the atmospheric lock holds. Everything else in this investigation flows from that number: the total rainfall under the flood arm, the cumulative heat stress on the crop, the grid demand days above critical thresholds, the number of levee sections sequentially stressed, the duration of mutual aid system depletion. The block's duration sets every downstream number, and as this investigation has established, that number is the one the models are least equipped to predict. Here are the 3 outcomes the evidence supports, presented honestly, without predetermined conclusions. Interpretation: 1. Short block, sequential stress. The system holds. The block establishes and persists for approximately 5 to 7 days within the shorter range of documented blocking events and the most common outcome in the historical distribution. The flood arm produces above normal rainfall across the Ohio-Mississippi watershed, but the training pattern doesn't fully develop before the block begins to break. River gauges rise above flood stage at multiple locations, but the cumulative rainfall total is insufficient to push the Missouri main stem into record territory. Some road closures occur. Minor levee overtopping is possible along sections identified as most vulnerable, but the event is acute, not sustained. The heat arm drives a single above normal temperature period of 4 to 5 days over the central U.S. power demand, rises above summer peak. Grid operators manage the spike through planned demand, reduction, and emergency reserve activation. Some rolling load reductions occur in the most stressed transmission corridors. Crops under the heat arm experience stress. Some yield reduction at locations where the heat wave coincides precisely with the corn pollination window, but the duration is insufficient to produce the basin-wide yield collapse documented in 2012. The USDA reports below normal crop ratings, but not a disaster declaration at the scale of 71% of the country. The block breaks when a major Rossby wave propagating upstream disrupts the blocking structure. The jet stream reasserts its westerly flow, the high weakens, the 2 flanking lows lose their energy source and begin tracking northeast. Within 48 to 72 hours of block breakdown, the forecast normalizes. Emergency management systems stand down. The damage is real: hundreds of millions in agricultural losses, localized flooding damage, some infrastructure stress, but the infrastructure systems that were designed to handle individual events absorb it. This is also the most statistically common outcome in the historical distribution of blocking events. Most blocks last less than 10 days, most of them resolve before the self-reinforcing mechanisms fully engage. Interpretation: 2. Extended block, partial compound, the system strains. The block holds for 10 to 14 days, within the upper range of documented summer blocking events over the continental United States. The specific mechanisms documented earlier in this investigation: soil moisture feedback on the heat arm, warm conveyor belt, latent heat feeding the flood arm's potential vorticity, have time to engage before external forcing can break the pattern. The flood arm produces sustained training rainfall over the Ohio-Missouri-Mississippi watershed for 10 to 12 days. River gauges at multiple locations along the Missouri and Ohio tributaries reach major flood stage simultaneously, the compound peak flow scenario documented in the 2011 event. Levee sections along the Missouri River that were flagged in Army Corps assessments as vulnerable are overtopped at 2 to 4 locations. The cascade mechanism begins but does not run to completion before the block breaks. Road closures affect multiple interstate corridors. Barge traffic on the Missouri and Upper Mississippi is constrained, not closed, but restricted, with weight and draft limits imposed. The heat arm produces 2 embedded heat waves within the sustained pattern, matching the 2012 structure that the Science Direct analysis identified as especially harmful to grain crops, corn yield across the heat arm's footprint falls approximately 15 to 20% nationally. USDA declares natural disaster in approximately 40 to 50% of the country. Food prices respond visibly. International commodity markets note the U.S. supply reduction. The power grid manages the demand spike through a combination of emergency conservation measures and managed load reduction periods, rolling blackouts in the most stressed transmission corridors, lasting 2 to 4 hours per affected area over a period of several days. The mutual aid pool for grid restoration is reduced, but not eliminated, because not all states are in simultaneous crisis. This is the scenario roughly analogous to the combined 2011 and 2012 events compressed into a single simultaneous occurrence. The system strains to its limits. It does not collapse, but it does not come through without revealing every structural vulnerability this investigation has documented. Interpretation. 3. Prolonged block, full compound. The system breaks. The block holds for 21 days or longer, matching the documented duration of the 2010 Russian event, the most destructive blocking event in the modern record. Every self-reinforcing mechanism has reached a maximum engagement. The heat arm has dried the soil completely, eliminated all evapotranspiration buffering, and driven the blocking high to its maximum intensity. The flood arm's warm conveyor belt is fully established, feeding latent heat into the blocking structure at altitude, reinforcing the potential vorticity anomaly that resists the jet stream's attempts to erode the block. The flood arm has been training convective systems over the Ohio, Missouri, Mississippi watershed for 3 consecutive weeks. Field capacity was exhausted in the first week. Every raindrop that has fallen since then has become direct surface runoff, into streams already at flood stage, into rivers already above major flood stage, into a levee system that has been under sustained stress for 14 to 21 days. The cascade mechanism, the progressive failure of upstream levee sections, adding hydraulic load to downstream sections, is running, not all at once, in sequence. Barge traffic on the Mississippi River is closed across multiple stretches. The river is not just high, it is actively destroying the infrastructure around it. Levees, roads, bridges, the port facilities that handle the export grain traffic. The Army Corps of Engineers cannot dredge its way out of this. The channel isn't silting up. It is flooded. The heat arm has now run for 3 weeks over the corn and soybean belt. The critical pollination window for the entire central and southern corn belt has passed under sustained heat stress. Yield projections are being revised downward in real time. The USDA is approaching a declaration equivalent to the 71% documented in 2012, but the damage this time is not tempered by the distribution system holding. The power grid is no longer managing. In the heat arm's footprint, demand has exceeded reserve capacity in multiple transmission corridors. Rolling blackouts are occurring in the major population centers under the heat dome: Dallas, Oklahoma City, Wichita, Kansas City, the cities where 68 to 100% of the urban population faces elevated heat illness risk during a combined blackout and heat wave, are experiencing both simultaneously. Emergency departments in heat-affected cities are receiving heat-related illness cases at rates straining capacity. The 12,800 death estimate for Phoenix alone is a number that applies, in scaled form, across every major urban center under the heat arm. Emergency management systems across the full block footprint are simultaneously activated at their highest operating levels. The mutual aid pool that the entire American emergency management architecture depends on is empty. There is no unaffected state to send resources from. The system is not just strained, it is running without a reserve. What determines which of these 3 outcomes materializes is a number. One specific number, how many days the block holds, and that number cannot be reliably predicted by any operational forecast model in existence today. The forecasters know all 3 of these outcomes are possible. They are not catastrophizing. They are running the physics forward, and the data they have access to, the 500 millibar geopotential height analysis, the ensemble spread, the soil moisture diagnostics, the sea surface temperature anomalies that research has shown can amplify the pattern's probability by a factor of 2 to 4. gives them a range of durations that spans interpretation 1 through interpretation 3. They cannot tell you which road you're on. Not yet. Not until the block has been running long enough for the self-reinforcing mechanisms to reveal whether they're fully engaged or whether external forcing is already beginning to erode the pattern. That uncertainty is not a failure of the science. It is an honest characterization of where operational meteorology currently stands at the edge of one of its most difficult problems. Strip everything back. No projections. No worst-case framing. No narrative construction. What does the confirmed data actually say about the state of the infrastructure that an omega block would challenge? The North American Electric Reliability Corporation, in its long-term reliability assessment released January 29th of 2026, projects that summer peak demand will increase by 224 gigawatts over the next 10 years, the highest compound annual growth rate since NRT began tracking this metric in 1995. That is a confirmed planning assessment from the organization responsible for overseeing North American grid reliability. It is not a climate model. It is a demand forecast. The Mississippi River and its tributaries move approximately 500 million tons of goods every year across a drainage basin covering 40% of the continental United States. During the 2012 drought, driven by the heat arm alone, without a simultaneous flood arm, the river was closed to barge traffic at least 3 times. The flow of goods was cut by 45% even before those closures. Every foot of draft lost means 6,000 fewer bushels of soybeans per barge trip. These are confirmed operational numbers from the Army Corps of Engineers. The PNAS research team, publishing in October of 2025, confirmed through supply chain analysis that U.S. food manufacturing is most sensitive to drought impacts in Nebraska, Indiana, and Illinois, and that those impacts propagate nationally, not regionally, through the agricultural supply chain. This is published peer-reviewed supply chain science. The FAS 2024 publication on grid failure under extreme heat confirmed that no coordinated interagency memorandum of understanding exists for managing a widespread multi-state grid failure coinciding with extreme heat. That is a documented structural absence in U.S. emergency planning. NOAA documented 28 weather and climate disasters in 2023, a new annual record, at a combined cost of at least $92.9 billion. Those were sequential events, each one drawing on the mutual aid pool that the Omega Block's geographic footprint would simultaneously exhaust. De Capua and colleagues in Nature's Climate and Atmospheric Science in 2021 quantified that sea surface temperature anomalies can increase the probability of the blocking wave train by a factor of 2 to 4 relative to what models predict. Models already underestimate blocking frequency. The warm ocean state makes them underestimate it by an additional factor of 2 to 4 on top of that. The University of Georgia research team, publishing in Nature Communications in 2023, documented that increasing jet stream waviness combined with declining North American snow cover is systematically favoring the formation of blocked high-pressure systems. The underlying physics driving this trend is ongoing. It is not reversing. These are the confirmed data points. Every one of them is named, sourced, and published. What they collectively describe is a margin, the gap between what the infrastructure systems can absorb and what an omega block at full activation demands. And the margin is narrowing on every dimension simultaneously. The grid's demand growth is outpacing its resilience improvements. The river commerce infrastructure was stressed to closure 3 times in a single event from one arm alone. The food supply chain's vulnerability nodes have been identified and quantified at the state level. The emergency management system's structural gap has been documented. And the atmospheric physics that produces blocking events is operating in an environment that makes them more likely, more intense, and harder for the models to predict with adequate lead time. The margin exists. The system is not on the verge of collapse on a normal weather day, but the margin has never been thinner at the same time as it has never been more exposed to the event that would test it. Here is what this investigation has established. An omega block is a documented, physically understood atmospheric phenomenon. Its mechanics have been known since Carl Gustav Rossby characterized the waves that drive it in the 1930s. Its compound structure, simultaneous flood arm, and heat arm, producing simultaneous catastrophes from the same mechanism, was demonstrated in peer-reviewed research by NASA's own atmospheric scientists based on the 2010 Russian-Pakistan event. Its damage potential to U.S. agriculture, river commerce, and power infrastructure has been measured across multiple historical events, each of which showed one arm of the compound at high severity. Its forecasting limitations are acknowledged in the peer-reviewed literature of the American Meteorological Society and the operational documentation of Skybrary. Its probability is being systematically underestimated by the models that are supposed to tell us when it arrives and how long it stays. The United States has experienced both arms of this pattern in the same year in sequence, 2011. It has experienced the heat arm at near maximum severity, 2012. Neither of those events produced the full simultaneous compound at maximum duration, but neither of those events was a coincidence. They were produced by the same large-scale atmospheric blocking dynamics, the same Rossby wave physics, the same moisture transport mechanisms. The full compound event is not a theoretical scenario constructed for dramatic effect. It is the natural result of those same dynamics operating at full intensity simultaneously, which is precisely what an omega block at maximum engagement does. The question this investigation cannot answer, because the data cannot yet answer it, is when, not if. The physics that produces an omega block over the continental United States is real, documented, and operating within an atmospheric environment that is making it more probable, not less. The infrastructure that would be tested by it is more exposed than it has ever been, on more dimensions simultaneously, with a narrower margin for absorbing the compound demand than at any prior point in the observational record. The question is when. We will be watching the 500 millibar geopotential height analysis on the GFS and ECMWF ensembles for the blocking signature. The high-pressure ridge building in the center, the two flanking troughs deepening, the jet stream being forced around the pattern into the omega shape. We will be watching the soil moisture anomaly maps for the Missouri, Ohio, Mississippi watershed, the silent amplifier that turns a severe event into a catastrophic one. We will be watching the NARC Regional Reserve margin reports for the heat arms impact zones, Texas, Kansas, Oklahoma, Missouri, where 68 to 100% of the urban population faces compound heat blackout risk under a sustained blocking event. We will be watching the USDA weekly crop condition reports in the corn and soybean belt, the first quantified signal of the heat arm's cumulative damage to the food supply. And we will be watching the forecast ensemble spread, because the moment the ensemble members begin diverging dramatically on block persistence duration, some resolving in 5 days, others showing 2 weeks, that spread is the model telling you, in the only language it has, that it is at the edge of what it can see. When it goes wide, we'll tell you. When the soil moisture maps shift, we'll tell you. When NERC issues its next elevated reliability concern, we'll tell you. Because the gap between what the data shows and what gets communicated to the families in the flood arms footprint who are watching their river rise, to the farmers in the heat arms path who are watching their soil crack, to the grid operators managing reserves they weren't supposed to need to manage in June, that gap is exactly where the most important stories live.
You are part of this investigation. Your comments, your local conditions, your observations about what the weather has been doing in your region, all of it informs the picture this community builds together. We will be here. We will be watching. And when the data moves, you will hear it here first.